We're now on day 18 of the 30-day SQL challenge, and we're going to be talking about normalization and denormalization today. Now, if you understand today's lesson, you're going to be able to design tables and databases that apps can write data into and dashboards can read data from. Now, most enterprises today suffer from a lot of performance-related issues. So if you understand today's lesson, then you're going to be able to solve most of them. And I'm going to teach you how to fix them. So let's begin. On days 15 and 16, every single join that you wrote assumed that the data was already split into sensible tables. So you have things like people in one table, or you had like addresses in another table. But the question is, who decides that split? And how do you even know when a table should be split or when it should be left alone? So this is the type of question that normalization actually answers for us. So if you want the entire video summarized into 2 sentences, let me just give it to you now. So normalization is when you split one big table into smaller ones. And denormalization is when you get a bunch of smaller tables and you make one big table out of it, or one view. So what I'm going to do is I'm going to walk you through both of them properly, and we're going to start with normalization. So normalization is splitting one big table or one wide table into smaller ones. So each table is focused on looking after a single fact. Okay, and when you do that, you're actually doing 2 things at the same time. Number one, it avoids duplicates. So that means the same fact stops being copied across row after row. And number 2, it keeps the data clean. So the table can never tell you 2 different stories about the same thing. And clean data is what lets you write safely in the first place. And when you talk about data rights or writing data, all that means is inserting records into a table or updating the database or deleting data from one. So if you want to do that safely and you want to do it consistently, then the best way to do that is by normalizing your tables. And all of that data splitting has one goal, and that's to store each fact in one place only. So that place is a small focused table, and it's not a large table. Because when you have large tables, the same fact can get copied over and over again. And by the way, a fact is just one piece of information that you store. So it can be something like a song and its artist, an album and its year, or a song and its genre. So in the database world, this is what professionals call reducing redundancy, right? And all that means is you're keeping a single source of truth. When every single fact has a single source of truth, there's only one copy that everyone can trust. And that means there's only one place to change anything if it ever goes wrong. So not 2, not 3, or 7, or 50. It's just 1. Otherwise, what's going to happen is the business is going to stop trusting those tables. And that's when data silos occur. So when businesses create their own business data sources, okay, like Excel workbooks, or maybe like text files that are pulled from a CRM, or even downloads from an FTP portal. So anytime we say a table is normalized or we're normalizing a table, it's simply another way of saying we're creating smaller tables, and each small table looks after one kind of facts. So just keep that in mind. So why is repeated data dangerous in the first place? I want you to picture us having, let's say, like a spreadsheet. And in this spreadsheet, you decide to record every single song you play on your phone. And of course, the spreadsheet is going to get bigger over time because you listen to a lot of music. So every single song is on its own row. And that's going to include things like the artist, the album, the release year, and the playlist that it belongs to. So when you're adding new songs to a new playlist, you have to copy the whole song block again and again. So for instance, let's say you spot that the album's release year was wrong. Okay, so instead of 1981, it should actually be 1982. And now what you have to do is you have to find every single row that it appears on. And now you have to fix it. Now, if you miss one row, so if you forget to update a single row, what's going to happen is your data is going to end up saying 2 different things about the exact same album. And you're not even going to get an error. You're not going to get any warning. All you're going to get is 2 versions of the truth. And that's going to live in one table. So a mess like that is going to create 3 specific problems. So in the database world, we call these anomalies. And these are things that break because the table was built badly in the first place. And it doesn't necessarily mean that the developers who designed it built it badly on purpose. All it means is that they didn't address these gaps properly while they were building the tables. Okay, so one of the first anomalies you're going to find is what we call the update anomaly. Okay, and this is when redundant data is stored in multiple places. Okay, and when we say redundant data, it just means that the same fact is stored in more than one place. Okay, so the same value is copied across lots of rows. So that's what we mean by redundant. Now, the problem with this type of issue becomes obvious when you're actually trying to update the tables in your database. So like I said before, if you try to correct an album's release year from 1981 to 1982, then you're going to have to manually find and update dozens of old records yourself. And if you miss one record, then now the data in the database is now inconsistent everywhere, because one record has 1981, another has 1982, even though it has pretty much the exact same facts recorded. And now you have two conflicting versions of which release year that album actually has. And then you have another problem called the insert anomaly. So this is when you actually cannot record a new piece of information or data because it's tied to another piece of information or data that doesn't actually exist yet. So for instance, let's say you want to add a brand new record or song that you discovered, like a new Ashake single. Now, because the table is built to record plays, so in other words, the songs you've actually played, the database might actually force you to input a playlist ID or like a position just to save the song. But what happens if you actually haven't created a playlist for this song yet? Because remember, our database, or rather our table, is storing the songs that we've actually played. But this is a new single, so we've not had the opportunity to even play it in the first place. So we can't add it to a playlist if we've never played it. So this is what we're talking about. The system won't even allow you to save the song yet, or even at all. And then the third issue is what we call the deletion anomaly. And now this issue is when you actually delete one record and then it accidentally wipes out a fact that was unrelated but actually important, and you actually wanted to keep it too. So for example, let's just say you want to remove a song from a playlist and you want to delete the record of that in your database. Now, the problem is this specific record also has the album's name and the year it was released to. Okay, so here's a problem, right? So let's say, for instance, you have Central C. Central C's released an album called Can't Rush Greatness, and he released this in 2025. And this record is the only one in our whole table that actually has this record. If we delete this record, then we're also going to delete the only record that has this information in our database. So the album data will now be lost forever. Now, if this table was designed properly from the very beginning, this issue wouldn't even exist, as well as the other issues we've just mentioned. Now, the funny part of all of this is that these three problems happen in almost every large enterprise on planet Earth right now. Now, if you understand this very well, if you understand this topic properly, then you can actually help them solve these problems before they seriously hurt them in the long run. Some companies are suffering from this problem right now. Others may be fine, but the problems will begin to emerge as time goes on. Now, the question is, how do we actually do it? How do we solve these problems? Because right now, it doesn't seem super obvious what the solution is. So how do we actually do this? How do we solve these problems? So we can clean the tables up in 3 steps, and these steps need to be done in the correct order. So one way of thinking about it, at least one way I like to think about it, is like a video game. Okay, so let's say you start a game on level 1 and you want to progress to the next level. The next level is only unlocked if you've cleared the one below it or the one before it. So each step builds on top of the step before it. Okay, so I call them 3 steps, but in the industry, we call them normal forms. And we're going to go through each normal form one by one as we progress through the video. So don't feel like you need to memorize everything at once. But I want to take you to PG Admin, and I want to show you something real quick. I want to show you what this messy data looks like in a real table. So what we're going to do is we're going to preview our messy music spreadsheet. It's going to be represented as a table. And then we're going to see the same song show up across lots of rows. Okay, so first of all, I'm just going to show you what this looks like. So I'm going to do select star from, and our table is called song plays. I'm going to run that. Let me show you what we're working with. So you can see the different columns in our table. See, we've got playlist name. So these are all the different names we've given to our playlists. So when you create a playlist, you can add different songs to it. this is the position it's in. We have song title, we have the artist, so whoever creates the song. This is the album that the song belongs in, and then the release year, so obviously the year that the song was released, and then we have the different genres. Okay, so we have all of this going on. But let's say we want to, so okay, let's just filter to, let's say, albums. Okay, so we said where album is, and we have a few albums going on. Okay, let's do Thriller. So let's run that. Okay, right, so we have 4 records that are returned for Thriller. So you can see that we have the same artist. You can see that we have the same album as well. You can also see we have the same release year, so 1982 for all of them. Okay, so the question is, what's actually different between these records? What's not the same? If you notice, you can see that we're getting different playlist names. So we have 2 for throwbacks and we have 2 for gym. Okay, so the only thing that changes really is the playlist name and of course the song. So you can see that the song title, or rather the song itself, is changing as well. So once again, the artist's name is the same throughout. The album is the same throughout. Release year is the same throughout. Okay, you can also see that genre is a bit different as well. Okay, but this is what we're talking about. Okay, we're seeing repeated data in a couple of places. You can see that Michael Jackson's been copied across every single row. Album's been copied across every single row. So this is the repeated data that we're talking about. Okay, we call it redundant data as far as normalization is concerned. So this is what we're about to clean up. Now we're going to be talking about normal forms, and we're going to explore all 3 normal forms that exist in normalization. There's actually many more, but in this video, we're going to be talking about the 3 most common ones. Okay, so let's stay on our example on the songs that we like to record into our spreadsheet. So as you can see in our table, we're recording different songs, and if you see the genre column in particular, you're going to notice that we're recording 3 values inside a single cell. So for example, if you look at Billie Jean, the song, next to it, you see the genres. You see pop, you see funk, and you see disco, right? Now, if you record all 3 values inside a single cell, you've actually just broken the very first rule of building a good table. And that's first normal form. Okay, so now, what is first normal form? What is it about? First normal form says that every cell must contain 1 value only, just 1 value. And all first normal form is trying to do is get rid of any lists, any tables, and any objects that are hiding inside your cells. So that means you have to keep breaking your data down until each cell in your table contains a single value. So with first normal form, really, there are actually just 2 rules in general. Okay, the first one is no cell can hold more than 1 value. So that means no cell is allowed to have any commas, and it's not allowed to have any slashes that squeeze a list of items into any cell at any point in time. Okay, so you can see right there, when you have pop, comma, funk, comma, disco, that's telling us straight away we have 3 values that are pretending to be 1 value. Okay, now the only exception to this rule is when you have a situation where the commas or the hyphens or the slashes are inside your cell and there are actually a legitimate part of the value itself. Okay, so for example, if you have double barrel names, okay, like for instance, let's say someone like Beyonce, okay, Beyonce's surname is Knowles Carter, okay, Knowles Carter, that's a double barrel name. Or like Mary Kate Olsen, so her first name's Mary Kate, that's double barreled. Or Trent Alexander Arnold, so his surname is Alexander Arnold, that's a legitimate name, that's 1 value as far as the system is concerned. So you're allowed to have hyphens in those cases. Okay, so, and by the way, the second rule of first normal form is that every row is unique. Okay, and that means every single table must have a primary key, and that way you can uniquely identify any row at any given time. So now the question is, when do you actually use first normal form? What situations qualify us to be using it? So you need to use first normal form whenever you're designing a relational database like SQL. Okay, and really, this is actually how you should be organizing your data in 99% of use cases anyways. Okay, and that's because when you keep each value on its own, it makes a couple of things very simple for you. So number one, it makes searching easier. Okay, so let's say, for example, okay, let's even go to PG admin very quickly. So, okay, for instance, let's say you have something like Python, comma, SQL, comma, Java. Okay, so let's say you have this. Okay, so if you ask SQL to find everyone who knows SQL, okay, it can't just sort or filter on this. And that's because the value is buried in the middle of a string. So this is a string. The value is buried right here. And in a situation like this, if this is found inside a database, so if I just make this like, let's say languages, let's just pretend this is a table, right? So in a situation where you're trying to find everybody who knows SQL, you're going to be forced to use a lot of complicated string functions just to pull out the term SQL or pull out the language SQL. Okay, and that's going to be very slow. And on top of that, you're going to be using a lot of complicated steps that don't even need to exist in the first place. And then the next thing is updating. So when you use first normal form, it makes it very easy for you to update data. So for instance, let's say you want to drop Java. So you want to get rid of it from your table. So now you're going to have to rewrite the entire cell just to do that. But if you had one value on each row, all you have to do now is just get rid of a single row. If everything's inside the same cell, you're going to also use a lot of complicated functions just to get rid of Java, because this is technically one value, even though it's literally 3 values. So the best thing for you to do is for you to break every single one into their own records. And that way, it's very easy for you to get rid of one record. Simple. Now the question is, when should you not use first normal form? Now, do not use first normal form if you're deliberately trying to store a list, or you're trying to store a table, or like a nested structure as one blob. Okay, and don't use first normal form if you actually don't need to query any part of that. So in that case, you actually do have a few other options. Okay, so one option you've got is to try using JSON format. Thankfully, PostgreSQL actually supports this inside your relational database. Okay, we'll explore that in a future video at some point. And another option you can try is a document database like MongoDB. Okay, so MongoDB is a non-relational database, or a NoSQL database. So these type of databases are designed to actually store lists, and they're designed to store tables and documents inside a single cell. And by the way, when I say long blob, like even a long blob of text is technically still like one value. Okay, so when you're talking about blobs like a paragraph, or like a text message, or like an audit log message, each of these actually qualifies as a single value inside first normal form. This rule only objects to a list of separate values that are squeezed into one cell. So not to any value that's simply just very long. Now, if you want to fix a first normal form violation, it's pretty much the same steps every single time. Now, the first step is for you to spot the violations in the first place. Okay, so what you need to do is you need to look through every single column, and then you need to find out which cells hold more than one value. Now, one way to spot this, at least one good way that I find in spotting this, is just find the columns that actually have commas in them, because that gives it away straight away. Okay, so literally go through the columns and check if there's a comma that's inside them. Okay, so even in this example, for instance, we were able to spot that this violated first normal form because we literally just saw commas inside them. And then we asked, are these 3 separate values, or is this just one value, one legitimate value? And you can see pop, funk, and disco are 3 separate values, and they're all hiding inside the same cell. Unfortunately, first normal form cannot accept this. And then the next step is to pull them out of that table. Okay, so these genres cannot stay in the song plays table. So we need to kick them out. And after that, we need to build a new table for these violations. Okay, so the violations that we highlighted need a new place to live. Okay, so we can give them their own new table where every single row has its own tag. So in short, first you have to create a fresh new table, and that's where we're going to store one row for every single genre. So one row per genre. And then we're going to add a column that links back to the previous table it used to live in. Okay, so the table that it used to live in is the song plays table. So we create a column that's able to link back to that or map back to them. And then when we do that, we're now in a position where one song with 3 genres actually have 3 rows. Okay, and now we're able to search, we're able to filter, we're able to join on individual genres. Okay, instead of using like complex strings and complex like functions to do the exact same thing. So this is actually making our life so much easier. That's the goal of all of this, is just to make our lives easier. So what we want to do now is we want to spot every single cell in the spreadsheet that has multiple values in it. And then when we do that, we want to now build a structure that actually aligns with first normal form. And by doing that, we're actually fixing the issues that we found. Okay. So number one, we're going to preview any offending column. That's the first thing we're going to do. And then we're going to create a separate genres table. And that's where we're going to get each genre its own row. Okay, we're going to give each genre its own record. So I'm just going to do the select statement once again. Okay, we'll do select star from, and then song plays. So let's run that again. Okay, and then this time what I'm going to do is I'm going to highlight the violations. Okay, I think it's worth me selecting specific columns. So I'm going to select song title. And the reason why I'm selecting specific columns is because I want it to be more focused. If I select all of the columns, then I'm going to be scrolling from left to right all the time. I don't want to be doing that. Okay, so song title. Yeah, okay. So, I mean, we've done it like this, of course, but an effective way, because there will be situations where you may not be able to do that. So for instance, you can see the first few records have commas in them, but there are some records that do not have commas in them. So in other words, they're not violating first normal form because there's only one value inside the cell. Okay, so look, where genre is not like, and I'm going to do 2 wildcards with a percentage sign. I'm going to add comma. So basically, I'm telling SQL, give me every single record inside the genres column that does not have a comma. Now, why am I saying the ones that do not have a comma? Because there's a strong chance that these records are simply just one value. They have one value inside them. And that means they do not violate first normal form. You can see that. So there are 3 songs that do not violate first normal form. So you see All Eyes on You, we have Time, and we have Don't Cry. You see that. But now we want to find the ones that do violate first normal form. So let's run this again. But we're going to now do where genres like, comma, with the wildcards. So we're basically telling SQL, give me every single record where the genres actually have a comma inside them. Okay. So look at this. So this has it, this has it, this has it, etc., etc. Okay. So you can see that there are a lot of songs that actually have 2 or 3 genres stuffed inside one cell, and they're all separated by a comma. So if I wanted to find every single song that had like funk in it, so every single song that was tagged funk, I can't just simply use the filter. It's not going to be easy. I'm going to have to use a lot of like string functions, and that's very slow and it's not reliable. And even it's impossible for me to index anyways. Okay, if I want to index it properly, that's not going to be easy either. So what we need to do is we just need to build a fix that gives every single genre its own row. And the best fix to do that is by giving it a completely separate table. Okay, so here's what I'm going to do. I'm going to comment this out. And then I'm going to use the create table command. Okay, so we're going to create a new table. Okay, and this table is specifically for song genres. Okay, so I'm doing that. Let's break it to a new line. So added parentheses as well. Now I'm going to give it a genre ID column. And then if you followed one of our previous days, I think it was on week 1, we were creating a bunch of tables, okay? And basically, every single time you're creating a primary key in pgadmin or PostgreSQL, use serial, right? Now, the first column is going to be the genre ID, of course. The second column is going to be the song title. And then you indent that. Okay, so the song title is going to be varchar. Now, artists, when they give in names to songs, it can be very long, it can be very short. So I'm going to say, give it 100 characters. 100 characters max for song title, okay? And also, a song title cannot be null. No nulls allowed. It can't be empty, okay? And then we're going to now include the genre itself. That's going to be varchar as well. Now, the genre, let's say 40. We're going to say 40. And also, we don't want it to be null. Okay, so that's pretty much all we need for this table. Now, if I just add the semicolon, and then I run it. So you can see we have 2 tables at the moment. If I run this, we're going to have 3 tables. And then if I refresh our table, and then let's even do a select start on it, you're going to see that there's nothing returned because we haven't actually inserted any data into it yet. Okay, so that's the next step. So I'm just going to do an insert into, and then I'm going to do song genres, right? Okay, and then I want to include data into song title and genre. I don't need to do genre ID because SQL is going to auto increment the primary key for me. So in other words, it's going to fill the primary keys for me. I don't need to focus on that. It's going to help me with that. I just need to focus on adding data to the song title and adding data to the genre. Okay, so the next thing I'm going to do is type in values. And I like breaking that into its own line. So, Billie Jean for the first one. So that's going to go under song title. Now, the question is, what genre am I including for this one? Pop, okay. And then I just copy this down. Let's just indent that. Okay. And then I'm going to change this one to funk. Now, I'm just going to fill the rest and then run the insert statement. So I'll see you in a second. Now, I've just completed the insert and I want to see whether it worked or not. So let's run select star from genres or song genres. You can see we now have a whole table dedicated to just genres. Okay, so if I also say order by, and then we can order by anything we want. So I'm going to say song title. I'm also going to say genre. So I run this. You can see that it's in descending order. So let me just add a semicolon there. Okay, so let's order by genre ID. You can see now Billie Jean has 3 separate genres tagged to it. And these genres are actually split on 3 separate rows, okay? And we have 1 clean genre each, as opposed to what we had before. So if you remember here, if you look at song plays, let's even say and song title equals, or rather, let's say song title is in Billie Jean and beta, because that's what we have at the moment. So if I run this and then I compare it to what we have here, I'm going to open up a new canvas just for this. You can see this is a clean representation of all the songs we have and their individual genres. And this is the old version. So this is the version that violates first normal form. And this is the version that now satisfies first normal form. So the question is, why does it satisfy first normal form? That's because every genre now has a single record or a single value inside each cell. Whereas this one has multiple values inside each cell. So this is violating first normal form. In other words, first normal form does not like this table. But first normal form loves this table because all the genres have one value only. So even now it makes it easy for us to do searches. So if you want to search for every single record that has funk or that is funk, we can do just that. We can't do the same for this one, no, because we're going to have to use different string functions just to pull out the funk. So that's funky. We don't want that. We like this one better. Okay, so there's a question that always comes up as well. So like, what about if you want to store like the whole track label inside one cell? If you want to store the whole track record, so let's say you want to store things like the artist or the album or the release year, can we not do that? And really, it's not necessarily a problem. You can do it if you want. So like, let's say for instance, your app actually treats it like a single label. So if it treats that as a single label, then yeah, it's fine to store everything inside one cell. Okay. So if it's like, if it's printing it on a sleeve or something, yeah, that's completely fine. The problem is if you ever need to do things like filter by year or filter by the artist, or you want to summarize by release year, or you want to sort by the album, okay, then that's when you should actually split it into its own separate columns or fields or records. Okay, so the test is really simple. The question is, does your application need to treat parts of this independently? If the answer is yes, then split it. If the answer is no, then leave it. So you still have this same music spreadsheet, but this time you're recording something new into it. What you're recording now is which song you played on which playlist. So for instance, we have like two playlists. So one is called Throwbacks and the other is called Gym. Okay, so Throwbacks contains the old classics that we love, and Gym is just the playlist that we run when we're working out. Okay, and you can now see that Billie Jean is found in both Throwback playlists and the Gym playlists. The question is, what makes each record inside this table unique? So in other words, what will be the primary key inside the song plays table? So it can't be the song and it can't be the playlist name only. Okay, because the reason why it can't be a song is because Billie Jean shows up twice. And it can't be the playlist by itself as well. And that's because the one playlist can have many songs inside it once you've played it. So in that situation, this is actually where you take both fields and you actually make it the primary key. So the song and the playlist. So remember, you can't do the song title alone. You can't do the playlist alone. You actually need to combine both of them together. Now, when you have two columns acting as one key like this is what we call a composite key. So a composite key is a primary key that's made up of two or more columns. So these two or more columns are combined to uniquely identify a record. Now, each record is identified by the pair. So in other words, when the two columns actually come together, you can't identify them as individuals. Okay, so you can't do it by the song alone, and you can't do it by the playlist alone. Both columns come together or are used together, and that's when they're considered a primary key. And that primary key is what we call a composite key. So the song title by itself is not a primary key. The playlist name by itself is not a primary key. It's when the song title and the playlist name are combining together. That's what makes it a primary key, also known as a composite key. Now, if you look at the artist column, right, and you look at both the records with Billie Jean in them, you're going to notice that both of them have the same artist, which is Michael Jackson. And that doesn't matter, no matter what playlist you're looking at. If you look at the first one, Throwbacks has Michael Jackson. If you look at the second one, it also has Michael Jackson there as well. And that makes sense because the artist is the one deciding what the song is. So Billie Jean is always going to be by Michael Jackson no matter which playlist it's in. And the playlist part of the composite key has nothing to do with it. So I say that for a reason. And that's because this actually violates second normal form. Okay, so what is second normal form? Second normal form means that every single column must depend on the whole key. It can't depend on a part of it. It can't depend on 50% of the composite ID. It can't depend on 70% on the composite key. It has to depend on 100% of it, the whole key. Okay, so I want to just quickly pause as well, by the way, because I keep using two phrases, and I want to make them crystal clear. So I always say one column depends on another one. You might hear me say it leans on another as well, but it means the exact same thing. So the question is, what is that thing? So it's actually simple. It's more simple than you think. So one column depends on another column when you know that the other column tells you this one automatically every single time. Okay, I'll give you an example. Okay, so let's take the artist and the song. If I asked you who made the song Billie Jean, you may be able to tell me who the artist is straight away, which is Michael Jackson. And you don't need to check anything else. Okay, so in that context, that's when we say that the artist depends on the song, or that the artist column leans on the song column. So either way, it just means that the song decides what the artist is or who the artist is. Now, the main goal of second normal form is to get rid of any column that leans on only a part of the composite key. Okay, so that simply means that if you looked at each non-key column one by one in a table, and they don't depend entirely on the composite key, then you have to drop them from the table. And the reason why you have to drop them from the table is so that you can create a fresh new table just for that. Okay, and also a non-key column, by the way, is just any column that isn't part of the primary key. That's it. So in other words, it's the real data that's in the table. It's not an identifier like an artist. So anyways, the two core rules for second normal form is number one, your table must already be in first normal form. Okay, so already every single cell holds one value. And number two, you're not allowed any partial dependency. Okay, so remember, every non-key must depend on the whole composite key. It cannot depend on just a part of it. And a partial dependency is when a column leans on only one part of it. So only one part of the composite key. So if it depends on 50% of the composite key, that's a partial dependency. If a column depends on 65% of the composite key, that is a partial dependency. If a column depends on 99% of the composite key, that is a partial dependency. Because the word partial literally just means incomplete or just a part of something. So for instance, the artist depends on the song alone and it has nothing to do with the playlists. So it depends on only a part of the key. That situation is not allowed in second normal form, no matter what. So we need to let it have its own table. But the question is, when do you actually need to use second normal form? So what situations qualify the use of second normal form? So you need to use it whenever your table's key is built from two or more columns. So any single time you have a composite key included, that's when you use second normal form. Okay, so if you do that, it's going to save you from duplicates. That's number one. And right now, you're going to keep seeing Michael Jackson again and again and again on different rows in your table. And that's because the artist depends on the song alone. So that simply means every single time the song lands on a new row, Michael Jackson gets copied in right alongside it. And that also means if you update it on one playlist row and you miss another one, then the same song is now going to claim two different artists. Okay, so for example, let's even say that you put my name in. So let's say if you update the playlists on one row and you say that I'm the creator of Billie Jean, so the artist is Steven. What's going to happen now is you're going to have one row that says Billie Jean artist, or the artist of Billie Jean is Steven, and you're going to get another row that says the artist of Billie Jean is Michael Jackson. So that means the table is contradicting itself. Now, if you store it once in its own table, then all you have to do is just one copy. You just have to maintain one copy. That's what you have to do moving forward now. And you wouldn't have that issue in the first place. You're not going to get a situation where data is contradicting itself because all you have to do is just maintain the table. the individual table. But we're going to get into all that later on. Because the question is, would you rather maintain several records across multiple tables? Or would you just rather maintain one copy inside one table? It's up to you. But the second thing that this does as well, by the way, is it saves your table from getting tangled. So at the moment, the details about the songs and the playlist that you're building are all jumbled up inside one table. If you pull each into its own table, then nothing's going to get mixed up in the first place. So a fact about a song is going to live inside the songs table. And a fact about a playlist is going to live inside the playlist table. But there are situations as well, by the way, where second normal form doesn't make sense. So when should you not use second normal form? And the good news is, a lot of the time, you actually don't need to use second normal form. Okay, so if your table has a single column key, then second normal form takes care of itself. Like if you think about it, second normal form is all about columns that depend on only a part of the key. But if the key is literally just one column, so it's literally just one column that makes up the primary key, then you don't have any parts to worry about because there's nothing to split in the first place. So for instance, the songs table, if you think about it, the primary key for the songs table would be the song on its own, or the playlist table. The primary key for the playlist table would be the playlists, and neither one of them have a composite key. So none of them can actually have a partial dependency in the first place. The moment you create them, that's when they're in second normal form. And most everyday tables have a single column as the key anyway, so second normal form is usually already sorted out for you. It's only when you have a composite key, that's when you need to stop and check, like this one. Now, just like the first normal form, you can actually fix any violation in second normal form with the 3 steps that we mentioned earlier. So the first step is just spotting the violations. Okay, so first of all, you have to split your columns into 2 groups. And you have to split it into the key and the non-key columns. So in other words, the keys that, or in other words, the columns that are not the primary key. So how do we know that they're the key here? So this time, the key is made up of 2 columns working together. So you have the song and you've got the playlist. So the question is, why both? Because neither one on its own identifies any row. So the same song sits on more than one playlist. So you have Billie Jean on throwbacks and you've got Billie Jean in the gym playlist. And every single playlist holds many songs, okay? It's only when you pair up this song on this playlist, that's when we can point to a specific row. So if you look at the example right there, Billie Jean and throwback together, that's what makes up the primary key. And then if you look at the second row, Billie Jean and gym together, that's what makes the primary key for the next row. That's what uniquely identifies them. Because if you look at Billie Jean on its own, it's not going to be good enough. If you look at the playlist by itself, not going to be good enough. But when you combine them together, that's what serves as a legitimate primary key, which is what we call a composite key. So the key is going to be the song and playlist pair. And everything else is just non-key. In other words, it's not a primary key. Now, all the non-keys, what you have to do is you have to take each one. And then you have to ask yourself one question. Do I need the whole key? So in other words, do I need both the song and the playlist, or do I need just a part of it? So here's the quick check, right? Does the value change when the playlist changes? I think what I'm going to do actually, let me show you, I'm actually going to quickly show you something. Okay, let's look at song plays again. Let's get rid of this for a moment. Okay, yeah. So this is what I'm talking about, okay? So the quick question or the quick check you have to make, you have to ask yourself, does the value change when the playlist changes? Okay, you want to determine whether each record actually depends on the whole key. Remember, the composite key is made up of the song and the playlist fields. So right now, the song is fine. So it has to depend on the song and the playlist. So, okay, so let's pick position, for example. Does the position depend on the song? The answer is yes, okay? That's because the same song sits near the top of one playlist and further down another. So the question is, does the position column depend on the song and the playlist? And the answer is yes. Now why? That's because the same song sits near the top of one playlist and then it can sit further down another playlist. Okay, no problem. Let's take the artist for instance. Does the artist column depend on both the song and the playlist? Now the answer is no. Okay, so and the reason why is because Billie Jean is by Michael Jackson on every single playlist. So the playlist actually doesn't do anything. So it needs only the song part of the key. So that sounds like it needs its own table. Now, how about the album and how about the release year? So that's the same as the artist actually, because they don't change with the playlist either. So when the non-key column needs only a part of the key, like this, that's what we call a partial dependency. And this is what second normal form does not allow, unfortunately. And because it doesn't allow it, the next thing for us to do is to pull them out of the table. So those columns have to go. So that's the artist and the rest of the song details. They can't actually stay in the table any longer. So we need to lift them out. So once we lift them out, we now need to do step 3, which is create a new table for these violations. Okay, so those song details need to live somewhere else. So we have to give them their own table, and the primary key for those tables is going to be the part that they actually depend on. So in short, it's just basically a fresh new table, and the primary key is going to be the song, for instance. And each song is going to be stored just once, and it's going to have its artist there as well. And the song is going to link back to the playlist that it appears on. And this is why we have the create table songs query. So when we do that, each song's artist lives in one row only. And now each song's artist lives in one row only. So what's going to happen now is if you have a situation where you want to rename an artist, then every single playlist sees the change at once. And that's instead of you copying the same artist onto every single row by hand. But we're going to go to PG admin and we're going to really show you what this looks like. So what we want to do now is we want to prove that the artist depends only on the song and not on the playlist field in the table. So once we do that, so once we prove it, we're now going to build a structure that stores each song's artist exactly once, because that's how second normal form wants it. So the plan is this, right? So what we're going to do is we're going to list every single song with this artist first, and then we're going to count how often that artist gets copied. And then after that, we're going to move the song details out into their own table. So let's do that straight away. So we're going to do select. Let's do select distinct, okay? And then I'm going to basically pick. I want the song title. Okay, so we've got song title. I also want the artist. Okay, and that's going to be from the song plays table. So these are the artists we're working with and their songs. Okay, so I also need to order by. So let's order by the song title. So I'm going to put 1. Right. So we have all our songs and we have the artists that each of them, or we have the artist that created each song. Okay. So we have 12 records, right? Okay. We get 12 rows back. So every single song maps to exactly one artist. You can see that. Okay. So even if you see something like Beat It by Michael Jackson, you have Billie Jean. So that's a map to Michael Jackson once. Okay, so if you notice, you don't actually need to know the playlist at all to work out who the artist is. So that's what we have right there. You don't need the playlist at all to figure out who the artist is. If you have the playlist, it will be very difficult for you to figure out who the artist is. But if you have the song, okay, it's a little bit easier. Because you know, Billie Jean was made by Michael Jackson. Okay, so if you look at Terminator, you know that was made by Ashake. If you look at Time, you know it was created by Hans Zimmer. If you've got Titanium, you know, or if you've got something like Unstoppable, you know that was made by Sia, so on and so forth. What we now need to do is to count how many times the same artist gets repeated. So that's the next step. Okay, so we already have song title, we've got artist. So now let's include a count. We're going to do count star, and then we're going to say, let's say times played. So how many times was this artist played? It's going to be from our songs plays table, song plays table. You also need to add the group by. So remember, add the columns that are not included in aggregate functions. That's what you add to your group by. At least that's the rule I tell myself. Okay, so once I run this, you're going to now see so how many times an artist gets repeated. So we're going to order by times played, and we're going to do this in descending order, so from highest to lowest. So let's run this. So you can now see the results. Okay, so we have a few. Okay, we have a few that turn up twice. Okay, so Michael Jackson, Beat It. So that's played twice. Billie Jean is played twice by Michael Jackson. Blinding Lights by The Weeknd. That's also played twice as well. Okay, so that sounds like this is once for each playlist that you added them to. So you can see that Michael Jackson is sitting against Billie Jean and Beat It twice. So on a real music spreadsheet, when you've replayed songs dozens of times, okay, if you've played it so many times, the same fact is actually going to be duplicated several times as well. So duplication like this, not only is it wasteful, it's actually dangerous. And the reason why it's dangerous is because if you update Billie Jean's artist on one playlist row, and then you forget to update it on other rows that may have the same information, what's going to happen now is the song, or that same song, is suddenly going to claim two different artists. And now you're in a situation where your table is contradicting itself without you knowing it. And then the only time somebody notices is when you're in a when the stakeholder is in a meeting and they see on the dashboard, right in the middle of closing a multi-million-dollar deal. And now that deal does not happen because no one can take the data seriously anymore. So it's high stakes stuff. So this is why we're taking these type of situations very seriously, because we're dealing with high stake situations that actually do happen in the real world. So things like that do happen. And we're trying to come up with fixes to prevent them from happening in the first place. Normalization is one of them. So, okay, how do we fix this? What's the solution for this? Now, the fix for this is to pull those song columns and pull them out and give them their own tables. That's the fix here. And we're going to create a new table. So we're going to create a table specifically for songs. So I'm going to start with the song title because that's what I saw there. Okay, so we're just going to do varchar in this case. I'm going to say varchar 100 primary key. Also, we're going to say artist. And then we're going to say varchar. Let's give this one not 40, let's do 80 this time. And of course, the artist can't be null. We have to, like, every single song has an artist. In other words, every song came from somebody, or these days something. You know, we're now in the age of AI, so it's very possible for AI to now be an artist if you create AI influencers and things like that. Okay, and then album, varchar. Okay, so for this one, let's say 120. We're not going to put not null because sometimes an artist can create a song and it may not actually have an album. So it's fine for it to be empty. Okay, let's create this table. So if I refresh this, it's going to go from 3 to 4. We have our songs table. Awesome. Okay, so the next thing I'm going to do is to insert data into it. Okay. Now, in this case, I'm going to do song title. Okay, because it's a string, I'm happy to add data into that. Okay, and then we're going to do artist, and then we're going to do album. Okay, and then values. Okay, so now the first value I'm going to add into this is actually, no, I don't. Hold on, I don't need to do that. I don't need to do this. Hold on. Oh, I can do this instead. I can do select distinct song title. So This is about working smart now. Why would I need to write it one by one when I can just do a select statement? Of course, literally. Okay, cool. Yeah. So, okay, before I run the whole insert into statement, let me just show you what I'm pulling. Remember, select distinct song title, artist, album. And I probably should make that a comma. Now, let me just show you what this looks like first. You can see we have a list of songs, we got the artist, and we got the album. This is a unique list of all of this. And that's what we're pushing into the songs table. That's it. So let's run that. Now, so that was basically a data migration, if that's what we'll call it. Select stuff from songs. You can see the exact same thing. That's what we've just done. Okay. So, okay, cool. We have 12 rows, okay? And now we have every single song exactly once. And each of these songs have their own artists and it's got the albums. Okay, so if we're now what we can do is if we want to rename an artist here, now we have the power to now rename an artist here. And we're not focused on, oh, do I need to update all the other tables and all the other playlists that have the artists as well? All I need to do is anytime I want to update an artist or an album, I can just do it inside this table without the worry or the overhead of figuring out all the other tables I need to update. One place saves everything. Okay, so I don't need to copy data across different rows. There's one place that has everything. It's a single source of truth for songs. So if I rename any artist in this list, in this table, every single playlist is going to see it at once. And the data doesn't need to be copied across different rows. So that's such a relief. That's going to save me a lot of time and effort. Now let's talk about third normal form. So at this point, every single row records a song that we've played, and it's got a little bit about where that song comes from. So alongside the song itself, we're also writing down the artist, we're writing down the album, its release year. And if we take Billie Jean as an example, so let's even say we did the same, let's even say we did a simple Google search in AI mode. And we're asking for the artist, we're asking for the album and the release year. In fact, let's do that right now. So let me just get Google up. Okay, so here I've got Google AI mode. Okay, so let's even try to ask it. Let's ask it a question, right? Okay, so I'm gonna say Billie Jean is a song, and then I'm going to ask it a couple of questions. Okay, so number one, who's the artist that made it? And then I'm gonna say number two, which album does it belong in? And then I'm going to say, what year was this album released? Okay? That's what I'm going to ask. So let's see what it tells me. Okay, so the song Billie Jean was created by Michael Jackson, and it was featured on his multi-platinum album Thriller, which was released in 1982. Okay, but here are the direct answers, right? So we have artist, Michael Jackson. We have album, Thriller. And we have the release year, 1982. So we can actually use these details to fill in like the details that we want on our side. But here's the main question I wanted to ask is, what actually decides that release year? Okay, so in other words, how can we tell what the release year is straight away? Okay, let's go back to our table. You can see the table here. What decides the release year straight away? If you look at the song, can you tell what the release year is? So if you look at the song, can you really tell what the release year is? We wouldn't really say the song per se, okay? And here's the reason why. Because the release year in our table is actually the album's release year, okay? The album's release year. Now that's going to be the year that the album itself came out. And every single song on the same album is going to share the exact same year. Okay, and I know you noticed Google AI mode told us Billie Jean was released in 1983. Okay, let me break it down. So if we take Thriller, right? So Thriller came out in 1982. Okay, so Billie Jean says 1982. Beat It says 1982. So every single track on Thriller says 1982. So the year doesn't change when the song changes. Okay, it's going to remain the same no matter what. It's only going to change when the album itself changes. So if we switch the albums, then the release year is going to change. If we switch the songs, probably not. So that's part of the reason why we're saying that it's the album that decides it. So if you know that the album is Thriller, then you already know that its release year is going to be 1982 every single time. And that's going to be true for every single song on Thriller, not just this one. So in short, the release year isn't about the song at all. It's actually tied to the album. And the album is just an ordinary column that sits inside the table. It's not even the key. So all of this breaks the third rule of a well-built table, and that's third normal form. Okay, so now what is third normal form asking for? So this rule actually tells us that every single column must depend on the key and nothing but the key. So in other words, no ordinary column is allowed to lean on another ordinary column to get its value. So the main goal of third normal form is to get rid of any single column that depends on a non-key column instead of the key itself. Okay, so any situation that an ordinary column depends on another ordinary column, it's violating third normal form, or the table is violating third normal form. Okay, so if you keep pulling columns out up. So for this one, you have to keep pulling columns out until every single one inside the table points straight to the key. You're not allowed any middleman field sitting in between them. None are allowed. Okay, so for this one, there is a piece of jargon that we use for this one. Okay, and let me even explain what that is. Okay, so we call this transitive dependency. Okay, so it sounds technical. When I say transitive dependency, it sounds like a massive word, but it's really not. It's quite simple actually. Okay, but it builds on the same idea that one column depends on another column, or one non-key column depends on another non-key column. So in short, the two rules for third normal form is that number one, your table already has to be in second normal form. So in other words, it's past first normal form and it's past second normal form. That's rule number one. Rule number two is you're not allowed any transitive dependency. So every single non-key column points directly at the key, never at another ordinary column. You are not allowed to point to any ordinary column. You must point to the primary key only. So the question is, when should you use third normal form? And the answer is, honestly, like almost every single time. You must always use third normal form, to be honest with you. Okay, that's the default you want to aim for nearly every single table in a relational database, especially the ones that run every single day transactions. Okay, and a transaction, by the way, is just one thing happening right now or something that's happened in the past. Okay, so, and it's being recorded into the database. So that can be an order you place, a payment taken, a booking made. So when you pull out these columns, it can actually help you do a couple of things. And the first one is sorting out hidden duplicates. So if you think about it, the release year sits against every single song on an album. So 1982 gets stamped onto Billie Jean's row, and then it gets stamped onto Beat It's row, and then it gets stamped onto every other Thriller row you've got. So if you corrected the release year, so maybe it was logged as 1980 or 1979, and it should actually be 1982. Now you're going to have to search through every single song on that album, and then you have to change all of them manually one by one. And if you miss one, then the same album is going to claim two different release years in your database, and now your data is contradicting itself once again. But if you just store that release year just once, and you make the album the key, then now there's only ever one copy you need to just get right. And then the second issue is just accidental loss. So it saves you from accidentally deleting data you actually want to keep. Now the question is, when should you not worry about third normal form? Now, there are times that you break third normal form on purpose, and it's actually completely fine. Okay, so for example, if you have like a front end tool that needs to read data very quickly. So if you have something like a form or like an app or some software of some kind, then you can actually leave these columns that are gatekeeping inside the table. And that's going to save you from doing any extra computation or joins if it just wants to fetch like maybe like the release year every single time. Or if you want to freeze a value in time as well, then you can do that. Okay, so for instance, if you want to keep the release year exactly as it was on that day, then you can do it. And so that any changes you make later doesn't actually rewrite your history behind your back. So both of those use cases I've just mentioned, that's what supports denormalization. And that's actually where we're heading to next. So just so you know, third normal form stands on its own. So a table can pass first normal form, it can pass second normal form, but it can still fail third normal form, just like this one did. Okay, so it's always worth, checking very quickly. So third normal form follows the same 3 steps like all the other normal forms we've just gone through. So the first step is just to spot the violations. So you want to split your columns into 2 groups. And the first one's going to be the non-key. Okay, the non-key columns, like any column that's not a primary key. So the question is, how do we know which is the key? How do we know? So the key is really the column each row is really about. Okay, it's going to be the one that once you know it, you can fill every other column, or you can fill everything else. Okay, so for instance, in this one, like each row is about a song, right? So if you tell me that the song is Billie Jean, then I'm more likely able to fill the rest, okay? And I may even tell you the album the song belongs in. And I could tell you the year that album was released as well. But the same approach doesn't work backwards for the others. Okay, so for example, if you tell me 1982, then that can mean anything. I can tell you hundreds of other stuff. Okay, I can tell you what year maybe like a football match was played, or maybe what political event took place that time. I can't really link it back to the song or the album or anything like that. Okay, so it's really the song that decides the others. So that's what makes the song the key here. So the artist, the album, the release year, these just describe the song. Okay, so they're the non-key columns. Now, if you take each non-key column and you ask yourself, which column do I need to work out what this is? So do I need the key? So in other words, do I need the song, or do I need another column first? Artist. So if I start with the artist, so what do I need to work out to figure out who the artist is? All I need is just a song. If I know the song, then I know who the artist is. So I just need to go straight to the key. That's fine. Okay, so artist is okay. So what about the album? Out of all of these columns, what do I need to figure out what the album is? Once again, it's just a song. If I know what the song is, I can predict what the album is. If I look at the artist, that artist could have released several albums. So I can just flick through so many other albums. So maybe not that. But if I look at the song, then it's likely only going to belong inside one album. So once again, straight to the key again. So that's fine. So what about the release year? So how about when the album was released? So the artist field doesn't actually tell me that. And the song alone doesn't actually decide that either. So that's the problem. In this situation, the song is not going to be enough. But the album does. And that's because every song on Thriller is 1982 for this album. So to get the release year, first you have to know the album, and then you're going to have to know the year it was released. So for this situation, we can actually say that it reaches the key only by going through the album. So it's really the album that's standing right in the middle. Okay, so that's the middleman. And that's what we call a transitive dependency. So once again, it's just a fancy name for a column that leans on middleman. So you're not allowed middlemen. No middleman columns are allowed in third normal form. So the next step is to pull them out. You have to pull them out of the table. So that column has to go. So the release year hangs off the album, and it can't stay in this table any longer. So we need to lift it out. And then once we lift it out, we have to build a new table just for it. Okay, so those album details need somewhere new to live. So we're going to give it its own table, and we're going to now convert the column key that they actually depend on into a key. Okay, and that's going to be the album. So that's what we do. When you do that, you're now going to see that each album's release year lives in one row only. So if you now correct a release year, then every single song under it now sees the change at once, instead of you copying the same release year onto every single row or song by hand. The question is, can we prove that the release year gets decided by the album and not by the song? Because that's what we're going to do now. We're going to have to figure out and prove it. Okay, so that's what we want to prove inside this demo. If we can do that, then we can now build a structure that stores each album's release year exactly once. Okay, so that's what we want to do. Okay, so how are we going to go about doing that? So what we want to do is we're going to list each album with its release year first, and then after that we're going to count out, and then after that we're going to count how often that release year gets copied. Okay, and then once we do that, we're finally going to now move the album details out into their own table. Okay, so what I want to do is I just want to run the song plays table, and I think I want to order by album. Okay, now let's, because I only want to select specific albums or specific records or columns. Okay, so I'm gonna want album, I'm gonna want release year. Let's do that. Okay, so let's do release year as well. Okay, and then we're ordering by album, right? So let's run that. This is what we get. So we have after hours on one row, after hours on another row. You can see that already. We're seeing duplicates. Okay. Maybe we should actually do. Okay, let's do select distinct because I want unique records. Yeah. Okay, that's better. Yeah. Cool. So after hours, all over the place, can't rush greatness, dreams worth more than money, and so on and so forth. Okay. So we get about 11 rows back. That's 11 albums, right? Okay. So each album maps to exactly one release year. You can see that After Hours is mapped to 2020. You can see Dreams Worth More Than Money, that's mapped to 2015. Okay. Now, if you notice, you don't actually need to know the song at all to work out the release year. Not according to this. You don't need to do that. Okay, because it's the album that decides it. Now, what we want to do is we want to count how many times the same release year gets repeated. Okay, so this is going to be, we're going to use counts. Okay, and then we're going to now say times repeated. We're going to introduce the group by. Album does not have an aggregate function. Release year does not have an aggregate function. Okay, so I'm going to run this. Also, let me even order by times repeated descending. Let's run that. You can see Thriller is repeated 4 times. By the way, we still have 11 records, you can see. Thriller is repeated 4 times. After Hours is twice. Nothing But the Beat is twice. This Is Acting is twice. Okay, so straight away, if I'm looking at Thriller, I already know that we have 4 separate records. And we already know that Billie Jean is twice and Beat It is twice. So that single fact, 1982, is sitting in our table 4 times over. Okay, so on a real music spreadsheet, like once again, if you have like loads of songs for each album, okay, so that single fact is going to be duplicated dozens of times. It's going to be duplicated loads of times. And like we mentioned for second normal form, like duplication like this is wasteful and it's dangerous. Because once again, if you're in a situation where we need to update Thriller's release year on one row, okay, want to update the release year, maybe even for a specific song. So if you remember, Billie Jean, the song itself was actually released in 1983. That was part of a marketing strategy, because back at the time, labels would basically release like maybe a couple of hits that would basically tease towards the album, and then they would drop the album. Now, when the album drops, and then it's now getting a lot of like like there's network effects. So a lot of fans are buying the albums and whatnot. Now, if you want to maximize sales, you now drop your hottest records after, and that's what happened um, with Billie Jean. So Billie Jean was actually released as a hit in 1983 by itself, even though it was part of the Thriller album. It was now released again in 1983 as a standalone hit, so that the label could maximize the sales and stay on top of the Billboard for as long as it possibly could in that period. And it worked. Okay. So in a situation like that, what if you wanted to like update the individual record for release year? Because the release year for Billie Jean the song is 1983. So what if you wanted to do that? Now, that's a completely separate topic. If you update the Thriller's release year on one row and then you miss another one, then what's going to happen now is that same album is going to suddenly claim two different release years. And it's now going to confuse people. So maybe they see 1983 in one, they see 1982 in another record. This is what happens when you have so many tables and you're trying to update multiple at the same time or at different intervals, but you forget to actually update maybe one or two that you just simply overlooked. Okay, so remember that's the update anomaly again. And your table is quietly contradicting itself. So how do you fix that? The fix is to always just create another table just for that. So in this situation, you want to pull the albums, the album columns, and create its own table, its own separate table. Okay? So create table, we're going to say albums, so album, and then we're going to say Facha. Let's even say like 120. Say primary key. And then we're going to say release year. Okay, so release year can be an integer. And then we run that. Now we've created a table just for that. We now need to insert data into that. Insert into, and then we're going to say albums. Okay, so similar to the other one we did. In fact, let's not forget include the columns we want to insert data into release year. Okay, so yeah, similar approach to the previous one we did. So for second normal form, so select distinct album and release year from song plays. So you can see a common theme here. We're basically inserting data from an existing table. We don't have to write it from scratch. So I'm running that. And then I'm going to now do a select star. Let's just figure out what is inside our table now. You can see all 11 records now exist, okay? So every single one of them now has the release year stored exactly once into it. So if we fixed a year here, every single song under it updates at once. So now every single album's release year is just in one place. So if we correct it once, then every single song under it is going to see the change. Just like that. That's how you want it. That's now satisfying third normal form. And also, by the way, like because we've covered so many normal forms up to this point, if you forget all of these normal forms, it's completely okay. There is actually a famous way to remember all three of them. Okay, so every single column must depend on the key, the whole key, and nothing but the key. So the first sentence, every column must depend on the key. That's first normal form. When we say the whole key, that's second normal form, and nothing but the key, that's third normal form. So it's almost playing like a courtroom oath. And that's the quickest way to recite or recall all three of these rules. So we started with one big table that was just a whole big mess. Okay, that's the song plays table. Okay, so with this table, it would have all the details about a song copied on every single row. And what we said was that this was a problem because if we needed to perform any data writes, okay, so if we want to update a row, or we want to insert new data into a table, or we wanted to delete any record from the database, what we're doing is also risking not writing data consistently across all the other places that the database would also need to be updated. So even if we did, it's going to be extremely slow and it's just going to be very expensive. So because of that, the same fact is sitting in dozens of rows. And that means that even if we made a small change, that change becomes dozens of separate values or separate updates. Okay, so what we said was, okay, let's normalize the data. Okay, and what we said was normalizing the data simply just means breaking down a large table into smaller tables that are easy to write data into. Okay, so first normal form was used to find the cells that had multiple genres squeezed into them. And what we did was we split them into their own individual rows. Second normal form was also used, and we used that to basically create a composite key by combining the song and the playlist fields. Then after that, we highlighted the fields that depended on the song part of the composite key, but not the playlist part of it. And once we did that, we pushed them into their own tables. So those columns that were doing partial dependencies, we give them their own tables. And then we use third normal form as well. So third normal form was basically used to figure out which fields did not depend on the primary key directly. So for instance, things like the release year. And what we did was we now listed them out and then we created a new table just for that. Okay, so we are now left with 5 tables that are actually focused. They're more focused and they're now storing every single fact once. So you can see playlist, playlist tracks, songs, albums, and song genres. Okay, so we have all of these tables available now. Okay, and now the anomalies are eliminated. So having something like this in place just makes it easy for us to write data into our database. So for instance, if we now want to correct the release year only, then we just change one row. And that one row is going to be in the albums table. So that's the third normal form fix. And if we delete a playlist, then we just lose that playlist and its tracking listing. But everything else, so the song, the artist, the album, the release year, all of that is safe because they're safe inside their own tables. So none of that knowledge is actually lost. So now we're in a situation where the same facts that used to be copied across several rows now just live in one place only, and the table can no longer contradict itself. So that's actually what we call a fully normalized structure, okay? Because every single fact is mentioned exactly once, okay? And you can see in the visual how we're now creating each of these tables. You can see that these columns are being lifted out of the big table, the big wide table, and we're now creating tables from that. So one wide big table becomes a couple of small focus tables. That's normalization right there. So we've just covered normalization. We've just said that normalization is just breaking one big table into smaller focus tables. And the reason why we do that is so that each fact lives in one place. And on top of that, we do that because we want to write data into our database better. We want it to be more accurate. We want to be more consistent across the entire database. But the thing is, clean tables actually come with a catch, okay? So there's always a cost to doing stuff like this, okay? So if you want to show something simple, like let's say a playlist that you've built, or the songs on it, or maybe even just the artists behind them, what you now have to do is to compute everything again. Okay, so you have to make all those joins like come together again. So you have to join the tables together, and then you have to wait until the joins are completed. And then you have to get your answer. So that happens every single time. So that's an expensive activity and it can be quite slow when you're doing that. So if you think about it, there's so many small tables you have to do that across. So, but okay, why are reads expensive? Why are they expensive in the first place? So keep in mind, by the way, if you're doing it like on a handful of rows, then these joins aren't actually a problem. So it's not a big deal, okay? Because you're gonna get the data back instantly. So like no problem there. But if you're reporting on a system that has millions or even billions of rows, then it adds up fast. And it's not even just the joins, okay? So every single time someone queries something, if they run something, okay, so that database actually has to redo the same heavy work every single time. So it has to join the tables back, it now has to group the rows, and then it has to run the aggregates. So whether that's a count, sum, average, and then it has to work out any calculated values on the fly. So once again, on big data, that's very slow, and it can actually cost the business a lot of money if you're not doing it correctly. Well, even if you are doing it correctly, it's still going to cost a lot of money because of the entire design. Like you're just doing it across several small tables that have millions of records, so it's going to take a lot of time. And imagine you do it, and it happens again and again on every single query. So if you're in a situation where maybe some of your queries are slow, it may be because you're actually doing this on normalized data. Okay, because you're forcing the system to do the same heavy work over and over and over again just to answer the same question. So situations like this is when you actually have to break the rules. You have to break the rules on purpose. But you only know what rules to break on purpose if you understand the rules in the first place, which is why I walked you through first normal form, second normal form, and the third normal form. So here's the trick. So instead of redoing all that work on every single read, why don't you just do the work once and then store the results somewhere? That's what denormalization is. Okay, so denormalization is basically just processing all your computation in a single moment in time. And then once you've done that, you now store the output somewhere that holds data. Okay, so like a table or a materialized view. Now, when you do this, you're deliberately adding the duplicates back into your table. Okay, so you are adding duplicates back in. Okay, so that simply means that you have to pre-join the tables, you have to pre-calculate the totals, and do that so that your tool just has to look up the answer instead of waiting and waiting and waiting for your table to be rebuilt every single time. Okay, so by the way, when I say pre something, okay, if I say pre-join or pre-calculate, so it's basically just doing it ahead of time. Okay, so before anyone runs the query, basically, instead of at that moment that they ask for the data. So when you do these pre-calculations and joins, it just makes it easy for the data to be read from these tables really fast because the data is ready. It's just ready. It's ready at the background. So it's just waiting for you to query it. So the moment you ask it, it's like, yep, here you go. But with normalized data, the data is not ready yet. So it has to now go back to the back of the kitchen and then get all the ingredients, get them together, and then do all its calculations and all its heavy work, and then give it data. That can take you time. Okay, so think about it like that. So if you want to think about it like that, so yeah, normalized data is basically you asking the waiter for food, and then the waiter takes your order down, and then the waiter takes it back to the kitchen, and then the chefs cook up your meal. And sometimes you're waiting 30 minutes, 45 minutes, and then you get your food. Denormalized is basically asking that same waiter for food. The waiter goes to the back of the kitchen and brings the food out pretty much instantly or close to immediately. And then you have your food, nice, fresh, and hot. So maybe that's an analogy that you could work with. Okay, so yeah, but the whole point is this, right? Like, if you want these fast data reads, then you have to pay a price for it. It comes at a cost. Okay, and that price is adding duplicates back into your table, like I said a moment ago. And yes, so that means the same duplicates that normalization was trying to get rid of in the first place is what you're now going to bring back in. Okay, so if your system reads far more than it writes, then that's a trade worth making. Okay, so but I noticed the pattern, by the way. Like, the difference between normalization and denormalization is basically just one simple question. The question is, what are we doing once so that we don't have to do it over again and again and again? So with normalization, what you're doing is you're basically just storing each fact once so that you never have to write it again. Okay, so that's what's going to make writing data faster for you. However, you have to accept that you're going to get slower reads. Okay, and you pay for them in joins every single time you query, or group bys, or aggregate functions, things like that. Now, denormalization does each calculation once, okay, and it does it so that you never have to compute it again, okay, and that's what's going to make reading data faster for you. Now, the price you have to pay for that is that you have to accept that your data will contain duplicates. You have to accept that your data will contain redundant information everywhere. If you're willing to accept that, okay, no problem. Okay, so it's basically the same instincts like in both ways. It's basically just doing the work once, not again and again. But you have to understand what you are trading away in return. So the simplest version of this is a view. Now a view is just a SQL query that you can save in your database. Now we use views so that you get one place to read data from without having to write out the joins yourself every single time. So the reason why we do this is because this is done so that dashboards read everything from a single place. And also you have to be, let me even be clear as well, by the way. A plain view does not store anything or make the data read faster, okay? It still runs the query underneath. The tool that actually stores the results for fast reads is a materialized view, okay? I'm going to cover that in day 25. So let's go into pgadmin and let's now work with the actual SQL query. Now, let's create a view. Okay, we're going to create a view. Now, this view is going to shape the spreadsheet's data that we've just flattened. And it's going to shape it into just one simple thing that we can read. Okay, so this shape is going to be suitable for a dashboard, right? Now, the question is, how do you create a view? First of all, you're going to see at the left of my panel, if you see the Object Explorer, I have no views. If I refresh that, you're going to see nothing's there. I'm just giving you a heads up, okay, because we're now going to create a view. Now, I'm going to type create view. Now, I'm going to call this, let's call this v playlist, and I'm going to call this v playlist log. And I'm going to type the word as. So this is how you create a view. You start with create view, type the name you want to give the view, and then followed by the word as, or the keyword as. After that, you type the query you want. So select star from song plays or whatever you want. Now, okay, so here, I want to also mention that generally speaking, you preface the name of your view with v underscore. Now, this is just so that it's easy to identify whether something's a view. If you have like a long SQL query and you're using views, it's very easy for you to spot views just by looking at the preface. So you see that v underscore is what we're using here. Now, in some cases, you're going to see some people use the suffix. So they may do something like this, playlist log underscore v. Okay. I personally like doing it at the front of the main subjects. So v underscore. So I preface with that. But yeah, whatever coding standards or styling standards suit your specific needs, do just that. Now, okay, so I'm going to include things like the playlist name because we're dealing with a playlist log, and then I'm going to do song title, and then after that I want to let's include artist, and maybe we want the album as well. Before I run the whole thing, I'm going to show you what data I'm going to put inside this view, or in other words, I'm going to show you what query this view is going to run. So let's run the select query only. You can see we have all sorts of playlists and the songs inside the playlist, the artist that made them, and the albums each song belongs in. Now, I'm going to now run the entire query and it's going to create a view for us. So let's run that. You can see we've now created the view. So let me refresh the views on the left. You can see we now have our view showing here. So if I go into our columns, you're going to see all the columns that we've mentioned inside our select statement within the view is now included here. So all I now have to do is comment this out, do select star from v underscore playlist log. You can see I'm treating it as a table. So I'm expecting this to run this select statement. You can see we get the exact same records as the select statement that's included in the view. Okay, so when we create a view, we can actually reuse it as many times as we want. And you need to remember, it's just a saved search. That's what it is. We've defined it once and it's a saved search. So whenever we want to read it like a table, we can do that. If you want to plug a dashboard into this, like Power BI or Tableau, we could do just that. Those options are now available to us. With every decision we make in the data world, there is always a trade-off. So in other words, if you want to enjoy something, if you want to enjoy a benefit, it comes at a cost. Now that cost may not be obvious, but there's always a cost in every decision you make. Okay. Now I say that to say this: which is better, normalized or denormalized? Okay, what would you think is the better option? The answer is neither, because it's a trade-off. Okay, so there's no right answer. Okay, if you want to say there's a right answer, the right answer is whatever your system does the most. So it's going to depend on what your system is using the most. Okay, now in saying that, you've already seen both sides. You see normalized. Okay, remember, normalized is built for writing. Okay, so what are the benefits of normalizing your data? Every single fact lives in exactly one place. Okay, and that means that your updates are fast, your updates are safe. Okay, because everything lives in one place. However, it does come at a cost. The reads are going to be slower. And that's because you're rebuilding them with joins, you're rebuilding them with group bys and aggregate functions every single time. So now, if you're querying a database that uses normalized tables, there's a strong chance you're going to be waiting for your data for a long time. You may be waiting and waiting and waiting, and that's because your tables are most likely normalized. So you're now telling the system to go to the back, make sure you join everything together, make sure you group the data accordingly, and then give me the results. That can take hours sometimes, and it's not good. Now, the next is denormalized. So that's all the data sitting together in one place. Denormalized data is built for reading because all of your data sits together in one place. Remember, it's like a single table. Okay, so all your data or all your reads are fast and they're going to be very simple because you don't really need joins. Everything's already together. So you don't have to wait and wait and wait for the data to now come together, calculate, and then you get the answers that you want. You don't need to do that. But it comes at a price. This is risky. If you're talking about writing data into denormalized data, it's risky business. Okay, the reason why it's risky is because the same fact is basically duplicated in so many places. So that means if you have to update data on a denormalized database, you have to make sure you're updating it everywhere. Now that could be complicated. That could get messy very quickly. So you have to know exactly what you're doing when you're choosing any one of these. Okay, but the real question is, how do you choose? Okay, so what's the process of choosing? Okay, so if you want to know like when to choose between normalized or denormalized options, there's a strong chance it's probably because you have a tool that's either putting data into something or it's reading data out of something. So you do need to ask one question. Is the tool that I'm using putting data in, or is it reading data out? So the first option is basically just to normalize it. Okay, so if you're dealing with like write heavy data, so in other words, if you're putting data into something, that means that data is flowing into that something. Okay, so data flows into something one record at a time. So for example, like that includes things like a form, a checkout, or an order on the screen, anything that involves people filling it in. Okay, so that could be write heavy. So when we say write heavy, it just means lots of data being written into a system. If your tool is write heavy, always normalize the data. Now, the other option is basically to denormalize it. Okay, so if people are reading answers out of it, that's read heavy. Now, read heavy just means that lots of data is being read out of the system. Okay, so examples, so you have a dashboard, you've got reports, you've got a BI tool. So in situations like this, just denormalize the data. Now, when we talk about the right side, the right, in other words, writing, Okay, not the right hand side, the right side. So when we talk about the right side, okay, that's your operational database, right? Okay, so that's going to record lots of small events as they're happening. Okay, so if you're talking about things like an order placed, or like how many steps you've walked this morning, or what searches you've made online on Google, you'll often hear the term OLTP. Okay, so that stands for online transactional processing. Okay, in other words, processing transactions on an online system, if that's what you want to call it. Okay, so things like Postgres or MySQL or like SQL Server, those are the systems that are built for things like that. Okay, so the right side, that's where recording small events happen as they occur. The past, the present, that's for online transactional processing. Okay, and next you have the read side. Okay, so that's online analytical processing, also known as OLAP. Okay, so systems like this is designed for answering lots of big questions. And the joins and the aggregations are already done ahead of time. So you're not doing it the moment you ask a question. When you ask a question, the calculations have already been done. So ask a question, you get your answer immediately. That's what OLAP specializes in. Okay, so these are the ones that sit on top of data warehouses. And these are the ones that actually feed dashboards and BI tools. So when you talk about Power BI or Tableau, this is the arena you're talking about. Okay, so the one thing you don't want to forget, the one rule that you never want to forget, okay, is the copy your reports read from is not the source of truth, right? That's just a copy of it. So denormalized data is not your source of truth, right? That's a copy of the source of truth. The source of truth, or the real source of truth, should I say, is going to be your normalized operational data. So the operational data that lives in the normalized layer. Okay, so even in the pipeline like you see right here, you can see that the app, you can see your front end tool is writing data into the normalized core. And then the normalized core and the denormalized copy, between those steps, that's where you're now processing the data, calculating it to make sure that your denormalized data is basically just a copy of the source of truth. That copy is what will get surfaced into dashboards and reports and any other tools that are used to answer questions for users. But let's now move into our exercise. So imagine we work in the National Statistics Office, okay, and they're running a count of the population. They do this every single few years. Okay, so they're going to publish reports on how many people live in each region, what jobs they do, and how the population is changing over time. So the database that they're working with is called Census Raw. And in the Census Raw database, there's about 20 records inside. So this is the information that they're giving us. Okay, and this is all counting the entire population across 9 households. And that's a recent thing they've just done. Okay, so every single record has like things like the house reference and address. It's got the district and the region, the person's name and relationship, and other important information that they want us to know about. Okay, okay. Now we are being messaged by someone called Amira. So Amira is basically the operations lead for the census. So if you remember the hybrid systems architecture diagram we just came back from, the one that had a normalized core to write data into and a denormalized layer to read the data from. That's actually what she needs. That's exactly what she needs. Okay, she wants us to do this with the census data, right? Okay. Now she's asking us to do this because she spot a couple of issues with her data, right? And she wants us to basically explore them and figure out a solution around them, right? So the first thing she wants us to do is basically explore the data, right? And once we've explored it, she wants us to split the data into tables and she wants us to structure them properly. And then once we've done that, the next task is to prove that this normalized structure works with joins. And then once we've done that, then she wants us to denormalize the data so that she can report on what's there and basically even compare the approaches. Okay. So the data we're going to be working with is the census raw. That's the table. That's the table that we are working with. Okay. So we're going to do select star from census raw. Okay, so this is all the data you can see. Ooh, it's a pretty wide table. Oh, yep. Remember the one big table. So straight away, we know the potential issues that could occur. You can see things like address line. Okay, you can see like the same address. Look. Okay, let me deselect that. You can see the same addresses occurring in places like this. Look, 17 River Lane appearing 3 times, 4 Hilltop Crescent twice, 89 Station Road twice, 6 Harbour View 3 times, and so on and so forth. So the address line's been repeated. You can see the district's been repeated. The region's been repeated a couple of times. You see North Region a couple of times, South Region a couple of times, so on and so forth. And look, it's quite a wide table. Okay, so this is a problem already. Just looking at this, like how many columns do we even have? That looks problematic. Yeah, it's a lot of redundant data. Okay. We're going to need to run a summary on this. I want to find out how bad the redundancy is. Okay. So we want to measure that. So, we want to count a few things. Okay. So first of all, yes, we want to count the total rows. That's one thing we want to do. But I also want unique records in this. Okay. And I think I want to go through this like individually. Look, I'm even seeing household references multiple times. So I want to see how many unique household refs exist. So I'm gonna call this unique household. I'm gonna call this. I think unique household is fine because this represents the household reference. Yeah. So let's find out how many unique households exist. What else do I want to find out? Districts is probably what I want to find out as well. Actually, no. Let's look at person name. Select distinct person name as unique persons. Okay, so let's even say unique people. So yeah, that's useful. Okay. What else matters to us? Okay, fine. Let's actually bring back districts as unique districts. Okay, cool. So unique districts. Okay, so what else do we want to find out? So we got unique households, unique people, unique districts. Okay. Okay, let's do unique region. We're just exploring the data, by the way. We're just getting to know what we're working with. Unique region. Maybe we should also do, I want to do something that isn't super obvious. Okay, let's do unique enumerator. Yeah, okay, so basically, I'm going to include enumerator. Oh no, that has to be caps. I need that consistency everywhere. Okay, cool. It's actually enumerator name as unique enumerator. Okay, yeah, cool. From it's gonna be from the census raw. Okay, so I am going to run this. This is what we get. So we have 20 records in total. Okay, so what these 20 records represent is we have 9 unique households. We have 20 people. Okay, so 9 unique households, we have 20 people. However, we've got 5 districts, we've got 4 regions, and we have 4 enumerators. Okay, that's interesting. So just looking at this alone, I can see the gap in the redundancy. Okay, so let me explain. Let me explain what I mean. Okay, so every single, like, even though we have 20 records, okay, we've only found 9 real households. And we've even found only even 4 real enumerators behind them. Okay, and by the way, enumerator, I probably should have explained earlier. So enumerator is just a field worker who collected the data. Okay, so anyone who's on the field and they collected the data, that's an enumerator. Okay, just for context. But yeah, so yeah, we have 20 records, we have 9 unique households, but we only have 4 like real enumerators. So basically, every single time 2 people live in the same address, okay, the address, the district, the region, and the enumerator, those details get copied as well. All of that gets copied, and that's waste in storage. Okay, so that's gonna be very difficult to keep data updated consistently everywhere. So what we now need to do is we now need to see if there are like any columns that have more than one value crammed up. So remember, first normal form violation. And I remember the trick to finding that is just figure out which fields have columns inside them. Okay, so I'm going to show you what I mean. Okay, so if I do select star from census raw, okay, let's just get all data back up. Okay, so what I'm going to do now is I'm just going to select the columns that matter to me in this moment. Person name, that's going to matter. Oh, languages spoken. I think that's going to be a useful one. Enumerator phone. Yeah, okay, let's do those 3. Okay. So this is just the EDA process, people. Okay, we're just exploring the data. We're trying to get to understand the severity of the issues here. Enumerator phone, is that correct? Yeah, okay, cool. Okay, first of all, a limit to that. Cool. Okay, now this is where it gets interesting. Okay, so these are the people, these are the languages spoken, and these are the phone numbers of the enumerators. All right, cool. Okay, so let's start with languages spoken. So where languages spoken is like, so in other words, it contains, and we add our wildcards inside single quotes, and I add a comma. I'm looking for only the ones that have commas inside them. So if you can see, if you see rows like this, there are no commas inside the languages spoken. That means one value is inside, because if there are more than one value, you're going to say one value, comma, next value. Just like you have here. So you have English, comma, Urdu. Those are 2 values. But let the system decide that. You can see, look at that. So you have English and Arabic for this one, English, Arabic for that one, English, Arabic, and French. You have English, Hindi, and Gujarati. You have English and Welsh. You got English and Twi, and so on and so forth. Okay, so you get the point. Okay, but we also want to include the ones that have multiple values inside the enumerator phone as well. If you saw that, it's actually excluded that. So I don't want to exclude any of that. So what we're going to do is we're going to use the OR operator. I'm going to bring this into its own line, and then I'm going to type in OR enumerator phone also contains commas. So any comma that shows up inside this column, I want you to return the values or the records for them. You can see, so you can see, okay, so for instance, in this situation, you can see that the language is spoken, English is actually a single value. But if you look at the enumerator phone column, this has multiple values. It's got one phone number here. You can see the first phone number there. And you can see the second phone number there. First normal form does not accept that under any circumstance. You are not allowed to do this in first normal form. So every single record you see here is a violation of first normal form. So I'm going to say highlight all first normal form violations, because that's what this is doing. That's what it's doing. So we need to At least we're aware, okay? We're aware because every single value should have its own row. That's the rule here. Remember, first normal form says every value must have its own row. In fact, actually, more specifically, first normal form actually says every cell must have a single value only. Now, every single row here is violating that. Look at this one. This does not have a single value inside it. It's got English and it's got Arabic. That's a violation. Look at the phone number 2. It's got phone number 1, phone number 2. Those are 2 values. That's violating first normal form. And this one too. So this column satisfies it because it only has 1 value inside the cell. However, this value violates it. Okay? Unacceptable, not allowed. This one violates it straight away. You can see we have 3 languages, 3 values inside this cell. Not allowed. You're not allowed to do that. However, this one only has 1 value. Okay? 1 phone number, that is. So we need to correct this. Okay? This needs to be fixed. It needs to be resolved. But at least we know. Okay? That's all this is about. We're just highlighting it. Okay? So what about let's even look at situations where third normal form is violated. Okay, so let's copy that. Highlight all third normal form violations. So how on earth are we going to do that? Let's do select distinct because I did remember the region and the region type, census raw. Yeah. Okay. All right, cool. So, yeah. This is another example. Okay. So, for instance, if I know, okay, first of all, let me break this down. Okay. So first of all, we have 4 regions in our results. Cool. Nothing crazy. So each of them have a region tied to a region type. Okay. So each region is tied to exactly 1 region type. So that's another way of saying that the region type depends on the region. It doesn't depend on the person, and it doesn't depend on the household. That's a violation of third normal form. Because remember, a non-key column is not meant to depend on another non-key column. Region type depends on region. These 2 are both not primary keys in the table. So what is the primary key for the table? In this example, just for the sake of this, look at this. You have record ID. So it's safe to say this is what it's meant to depend on. That's what it's meant to depend on. If it's not depending on that, then it's a third normal form violation. And as you can see, this can be determined by this. So the moment you know what West region is, you sort of have an idea what urban is. If you say West region, okay, that's urban. The region type is urban. If you say East region, okay, that's coastal. If you say South region, that's in a rural area. You know, something like that. Okay. Anyways, so now before we've touched anything, we have an idea of what violations exist. So we can actually begin with the task properly. So task 1, split into 6 normalized tables. Okay, so we're going to restructure this messy table, this census raw table. We're going to restructure it and we're going to break them down into clean normalized tables. Okay, we need a clean set of tables. Okay, so we're going to build them up a few times, and after each one, I'm going to tell you exactly what they're doing. Okay, so one thing you have to keep in mind, by the way, is we're going to create the parent tables first. Okay, that's the first thing. And then we're going to build the child tables. And that's because a foreign key needs the parent table to already exist before the child can point towards it. Okay, and if you remember, in our previous lessons, we touched on primary keys, foreign keys, and things like that. So a foreign key is just basically the column in the child table that points back to its parent table. Okay, so we're going to now start with the table that fixes our third normal form problem. Okay, that's the regions. So let's go back into PG admin. We're going to create a new canvas. And what we're going to do is create a whole new table, because you can't have a situation where the region type depends on the regions. Third normal form cannot take that. It breaks its heart. So let's fix it. Okay. So we're gonna call this census regions, and then we're going to maybe what do we have? Okay, we have regions. Okay, so we have region, and we had okay, let me just first type this in. So varchar. Okay, and by the way, guys, it's okay for us to use varchar as the primary key. Okay, because we don't always want to auto increment. If you remember, we used to use serial to auto increment the primary key, but we don't need to do that every single time. Okay, especially if we're creating tables like this. At least for the sake of this exercise, let me be very strict. For the sake of this exercise, okay. It's not a rule of thumb. It's just something to just keep in mind. Okay. Varchar. Okay, and then let's say 50. Okay. So region type 80, or it's rather region have 80 characters. Okay, that's completely fine. Varchar can have 50. Okay, so let's run this. Cool. Okay, so we have a table. Okay, so if you remember, the region type depended on the region, not on the person. Okay, and it didn't depend on the primary key of the census table either. Okay, so what we need to do is we need to give the region its own table, and then we're going to store each region's type exactly once, right? So we've done that now. We've created this table. So if I refresh the tables, you're going to see census regions right there. Okay, cool. So the next thing we need to do is create a table for households. Okay, so let's create table. I'm going to call this, let's call it census households. Okay. Now, let's have a look at the data once again. Okay, so we need to basically lift this out. You can see that's character variant, so it's varchar anyways. Address line needs to be lifted out. District, yes, that needs to be lifted out. Region, yes, region. What else? I think that's it. Okay, no, census state as well. Okay, yeah, okay. So all these columns need to be lifted out. So let me just I think the easier way to do this is for me to do like this. Let me write them out here first. Household ref, and then address line. So I remember district, and then region, and then census date. I believe that's the format it follows. Yep, cool. So these are the columns we're lifting out of the wide table. And we're going to create its own table. You see? We're creating a table just for that. Okay, but we're not done. We're going to give it its data types, of course. We don't want to leave it naked. So you have to give it its data types, okay? So varchar 20, primary key. Address line. This is also going to be varchar. Okay, and this is going to be, addresses are long, so I can't say 20. I have to say 200. Yeah, okay, cool. The district. Okay, so a district, maybe like 100 characters, something like that. Probably 80 actually, let's just say. Region could be similar. It could be 80 as well. Oh, let's close that. Census date. Okay, so census date, that's just dates. Okay, let's just keep it that. Cool. Oh, by the way, we're mentioning region, right? We've just created the region table here. So we're mentioning region. So we're mentioning region inside our census regions table as well. So we actually have to include a reference back to that table. Remember, the parent table and the child table. Okay, so I'm going to type in references. Okay, so I need to point this field to the parent, which is here. So the parent table is the census regions table. And that's what's going to contain the region that I want this one to be referencing. So what I have to do is type census regions. I mentioned the table first. After, I use the word references. Right after, I mentioned the data type I want for this specific column. Okay, so first of all, I create the column inside the table, the child table, if you like, and then mention the data type. And after that, I mention the word references. And that's what's telling the system that this is a foreign key because this is a primary key. Now, okay, let me mention the name of this key. So I'm going to type in region, okay? And that's it. That's all I do. Okay, so now it's going to be pointing towards this table. Cool. So that's wonderful. So I run this. And I've also created that table. So if I refresh the tables here, we now have 7 tables. Awesome. Okay, so the next thing we also want to create would be the census persons table, because that was the other violation that we noticed. Okay, and yeah, let me spell that correctly. Census persons table. So create table, census person or census persons, and then once again go back into the original table, this one wide table that we're trying to normalize. Okay, what person related data do we have? Okay, we got person name. That's something. I mean, to be honest, household reference, because that's related to a person. We're gonna want that. What else do we want? We're gonna want the actually for this one, what we want is the person's name. Household ref, yes, we want that. Because it has to be specific to the person for now. Yeah, we want the relationship. The date of birth of the person will be useful. Their gender, the occupation, of course, and we want their ethnicity. Okay, so that's I think that's enough for this. We're leaving languages spoken. Okay, because we're going to deal with this table. I mean, this column. We're going to deal with that in a moment. Let's just focus on these ones. Cool. Okay, so okay, let's do like this here. These are the columns we want to lift and move into their own table because they're violating normal forms. Okay, cool. Person name. Oh yeah, let's do household ref and then relationship. Okay, let's scroll to the right. Yes, date of birth. Date of birth. We've got the gender, occupation, and the ethnicity. Yeah, and no, we don't. No, not needed. No censor dates. Cool. Let's go back to creating the table. Yeah. All right then, and we're going to need for this one. We're actually going to need an incrementing column that serves as the primary key. This is important for this one. Okay, so serial primary key. So that's what we're going to do. For household, actually, for person name, it's going to be voucher. Okay, so this one's going to be 20. Now, person name, that's going to be voucher. Okay, we're going to do voucher of 100. That's going to be not. Aha. Now, for household reference, this one, okay, so this is going to be voucher. We're going to say 20. Okay, now this is going to be references once again. And we're going to be pointing to the census household table or the census households table. Okay, if you see, household ref is the primary key for the census households table. So therefore, this is going to be the foreign key inside the census persons table. Okay, so census household, or households, keep saying household, it's plural. Okay, and then we're going to be saying household ref. Okay, so officially we're now pointing to this table. That's what we're doing here. Okay, awesome. Okay, now relationship, that's going to be varchar. Let's just say 50 for that. Okay, date of birth. So date of birth is going to be dates, of course. Gender will be, let's say varchar. Let's just say 20. Occupation. So varchar. Let's say 50. I think 50 will be fine. Okay, let's just say 100. 100 just in case. Ethnicity. That's going to be varchar as well. And for now, let's just say 80. Okay, so I'm going to add a semicolons. I should be added semicolons at the end. Okay, let's run this. And then we refresh the tables. And now we have 8 tables. Okay, I have 8 tables. Maybe for the sake of I just want to keep everything clean. So let's just drop the tables that we used before. Drop table albums. Let's just delete the tables that are not necessary for this exercise. Song genres. Then song plays, and then we just have songs. Okay, so let's drop all of that. Okay, so in this case, I'm going to say cascade. Okay, let's just add cascade at the end. Okay, it's always important when you're done with the activity, just add the drop table statements so that you're clearing all of your data. Okay, so I need to also drop view, v playlist log, cascade. Okay, I think we're good. Hold on, let me just refresh that. Okay, awesome. Yeah, so we have just the data or the tables relevant to this lesson. Cool. So we've created 3 tables, and that was all based on the information that we saw on census raw. Okay, cool. So we have our tables, but we're not done just yet. Okay, so what we need to now do is we need to apply a second normal form fix. Okay, we've created a couple of tables, but we're not done just yet. Okay, what we want to do now is just to make sure that every single household stores its address just once. Okay, not once per person living there. Okay, and also every person links back to their household with a foreign key. That's what we actually want. Okay, so because this now means that the details about any person is not going to drag the whole address along with them. That's what we're trying to avoid. We don't want to do that. Okay, so now the first normal form fixes the columns that had a list crammed inside one cell. Okay, so we have to create tables just for that. So these are basically, you can say that they're fixing, I guess you can say they're fixing second normal form violations. And now we want to create the tables that are fixing first normal form violations. So if you remember the languages, that's why I said I want to deal with languages separately. So create table, and we're going to basically say census languages. Now for this one, I'm going to say language ID, and then I'm going to give it a serial primary key. We want this to auto increment the primary key for us. Okay, so we have language ID. Now the next thing we want to do is we want to do person ID. Okay, now person ID is going to be integer, and this is going to reference, okay, it's going to reference another table. So it's going to reference the census person. You know what? I think it actually makes sense for me to just pull this at the bottom. Just that I want you to be able to see what I'm talking about. Okay, so never mind it being in order like that, but let me show you what I'm talking about. Okay, cool. So the person ID, look, if I just double click that, you can see person ID actually appears inside this table, the census persons table. That's what I want to point you to. So I'm going to say census underscore persons, and then I'm going to mention the primary key of that table. So it's person ID. And that's all I need to do. Simple as that. Okay, so now we have a foreign key inside this table as well, which is the person ID. We have a primary key, which is the language ID, and we have a foreign key, which is the person ID. Now, we're also going to include a language, okay, and that's varchar. Okay, and well, this is going to be, let's say, 50. Remember, one language. We don't want it to have nulls, no empty values, please. No nulls, you're not allowed to do that in this table. Okay, so running this is going to fix the first normal form violation. Let me just create more space and then run this. We've now created this table. So let me refresh that. Table number 5, we have a census languages table. Okay, so we're basically trying to create a table that gives each language its own row. That's the goal here. Once we've done that, we can now link them back to the person who speaks it. That's the reason why we're doing this. So that's why we're linking the tables together. Okay. So the next thing we need to do is basically create a table for enumerators, and want to also create a table for the numbers of enumerators. Okay, so let's do that. Okay, so I'm going to speed this up so that we get right to the end. So I'll be right back. So we now have the query for creating tables for enumerators. First, the enumerator people and the enumerators phone numbers. So I'm going to run both of them right now, and it's going to take our table from 5 to 7. You can see we now have those two tables included. Okay, so in total, we've now created 6 tables. Look, 1, 2, and 3, and 4, and 5, and 6. 6 tables, okay? Now, the thing is, these tables are actually empty. There's nothing inside them. All we've done is just built the structures. So what we now need to do is migrate the data across. I'm going to do that one at a time. Okay, so we're going to follow the same pattern as we've seen before. We're going to basically pull the distinct values out of the messy table, and then we're going to drop them inside the clean ones. That's how we're going to migrate the data here. Okay, so what I'm going to do is create space at the bottom here, and I'm going to write the insert statements. I'm going to show you like one, and then I'm just going to speed right into the end. So first you type in, okay, so let's say for instance, I'm going to start with census regions. Okay, let's start with that. That's the first table I see. Insert into census regions, right? Okay, and very quickly, let me just remind myself what's inside here. Okay, it's called region and region type. So that's what we want to insert data into. So I'm going to type in region, and I'm going to type in region type. Okay, so after that, I'm going to select distinct, the same columns, region and region type. Okay, this is going to be from the census raw, because that's the main table we're doing all of this from. Okay, so if you want, you can also indent that for visual hierarchy, but basically this is just migrating data from the one wide table into the small focused table. That's what we're doing, and we're going to be doing that throughout the entire throughout the other tables that we're trying to migrate to. Okay, so let's run that. So you can now see that there is data inside this table. Okay, so we've now used distinct because every single region should land in the table only once. And we've migrated that data into our empty table, what was once our empty table that we created earlier. Okay, so basically I'm going to do the same for all the other tables, and then I'll be right back. Okay, so I've now finished inserting the data into all of our empty tables. So now what I'm going to do is I'm now going to basically combine all of the tables together using the union all, so that we can see the total data that exists inside each of them. Okay, so how many rows exist across all those tables. So what I'm going to do is I'm going to type select statement first, and I'm going to start with census region. Okay, so I'm going to call this table name. That's the alias I'm giving it. And then I'm going to do a count. And basically this count is just going to represent row counts. Okay. This is going to be from census raw. And then I'm going to use union all. And then basically follow a similar process. But I've already established the aliases at the beginning. So I don't need to establish the aliases for the second part of the query. So I can just go straight into calling this census. And then for this one, the second table was household or census households. Okay. And then I could just do count star. Just do caps for consistency. And then union all. And so on and so forth. So let me just complete the rest. And then the third one is census persons. Then that's counts. Union all. So the fourth one. So I'm just going to copy the rest. Alright, let me do like this. Do like this. Okay, but you have to be careful when you're copying data like this. You have to be real careful. You have to know exactly what you're doing. Otherwise, you're going to get redundant data, duplicates, inaccurate data, and you want to avoid that at all cost. So concentration is one of the most important things in doing things like this. Okay, now this is basically enumerators. Phones. Yeah. Okay. So that's basically everything I want. Oh, also, I think it's safe to say each of these need to come from a table, right? Yeah. Okay. That's also important. Let me just paste that first. Okay. Now, census persons, census languages, census enumerators, phone numbers or phones. Okay, cool. So I'm going to run this. You can see what I'm working with here. You're going to see this total count operate right now. Let's run this. What would I call it? Oh, enumerator phones, not. Okay, let's do that again. Yeah, okay. So you can see what our union all has given us. So look at this. Okay, so census region. So this actually tallies up with what we got from the beginning. Where is my yeah, let me actually do I'm gonna do a screenshot. So let's just screenshot everything here. Okay, so let's go back to this. Maybe I should have done the other way around, but it's all good. Okay, so I think, you know what, I'm not even trying to be extra, but let me just do it like this. And then go back to this. Cool, okay, cool, awesome. So we can see that this actually matches the results we got earlier. Look at that. So very similar to the results that we had inside our EDA. Okay, so all the 20 people still exist. You can see here, total rows 20. Okay, and those are 20 people. right? We kept every single one. Look at the unique households. You can see in our EDA, we got 9. And in our data here, we got 9. You can also see that enumerators is 4. Unique enumerators from our EDA as well is also 4. Okay, and so on and so forth. So this is great. Look, they both match. Oh, yeah, so I was looking at regions, but census persons, okay, yeah, just like that. Awesome. Okay, but the point is this, okay, everything does look like it matches, right? But even if you look at let's go back to this. You can see that languages is 34 and enumerator phones is 5. So in other words, there are more rows than there are people in or enumerators in general. Okay, so that's telling us straight away that the first normal form fix that we applied is now made visible. Okay, so every single language and every single phone number that used to be crammed inside one cell has its own rows. That's what that's telling us now. Okay, and yeah, once again, let's even show you the data itself, right? Let's go into year. So even this, I'll show you. So you can see every single row has its own data. You can see it has its own language ID, its own person ID. You see? It's now split into their own rows, their own records. Okay, and that's awesome. Okay, so census households. So this is the normalized data we're talking about. Every household reference has its own address line. It's got its own district, region, census date, so on and so forth. Okay, if you see census persons, you see everyone's uniquely identified now. You see that? We've now split that big table into smaller tables that we can now manage. Okay, so that's actually good because that means every fact is now stored exactly once. Okay, so we don't have any redundant information anywhere now. Okay, you're not finding cells that have commas inside them. And that means first normal form has been fixed. Number 2, query the normalized structure with joins. Okay, so Amira wants to see the data back together. Okay, so that means we're going to start using joins. Okay, so what we're going to do is we're going to now pull data from 3 separate tables and we're going to assemble them into one result. So that's exactly what joins are all about. So let's begin. And it's now time to join data together. We now have separate tables. Okay, we have normalized tables, meaning we've got a lot of small tables to work with. So the question is, how are we going to go about doing this? So we do have the census persons table. Okay, so we can give an alias of P, right? Okay, fine. Let's run it first. Okay, better. Okay, so cool. We got this table. Now, what other tables do we want to join to this? So first of all, what do we want to see? What information do we want to see here? Okay, we're going to want to see a person's name. Let's look at the relationship. Okay, and we can also look at things like the occupation. Okay, let's start with that, right? Person name. So we start with the alias. We gave it an alias of P. Add a full stop. So we're telling it pull data from the census persons table. And then we type in the relationship and then the occupation. Cool. Okay. So that's quite cool. Now I think we should do an inner join on the census households. Let's call this H. Well, what can we use to join these 2 tables together? Let's even expand the census households columns. So this has household reference. That's the primary key that it's got. And I'm pretty sure, yep, this has household reference as well. So we can join right on that. So P equals household reference, and that's going to equal H is household reference. Thankfully, they're the same name. Okay, what columns does it have? Okay, so from the households table, what do we want? I'm sure we can pick things like district. Can use region to show us the region, and like you know what? I think maybe that's fine. Okay, district is fine because I want us to join on other tables. In fact, the region we've got a table specifically for that. So let's just take advantage of that. So census regions is right here. So let's expand the columns. We can pull the region into this. So okay, so instead of that, let's use the one for region. That's a good alias actually. Let's give it an alias of R. We're going to join on. Okay, so if we're going to join on this table, we're going to now need to take advantage of the ID inside this table. The ID, or the unique ID inside here, is the reference, or it's the region, should I say, our region. Thankfully, this has a region column too. So in other words, the census households table has that as well. So we can join on that, which is brilliant. And in fact, we can, if we're pulling region, we might as well pull region type. Okay, so yeah, that's what we're working with. So you can see the two joins we have. Yeah, so that's awesome. Okay, so if we're going to order by, so the question is, what do we want to order by? We can order by the H household reference, and we can do it in ascending order, doesn't really matter. And then we can do it by the person's name. Okay, so let's run all this. I think it's regions actually, regions. So yeah, let's run that. Okay, so this is what we get. So we get about 20 records back. Okay, so yeah, showing us the person, it's showing us information about their household. Okay, it's telling us things about their district, their region, what type of region do they live in? Okay, what's the occupation of every person within those households? Okay, so remember, the census person or the census persons provides details about the person. Okay, and then you have the census households. Okay, that's giving us information about their address, right? And then you have the census regions, which is giving us information about the region and the region type. Okay, and once again, the key thing is this: every single fact is coming out exactly once. That's the key theme here. Okay, so let's say, for instance, if the region type changes, then all I'm doing is updating one row in the regions table. That's it. And every single query that joins it gets to see the new value automatically. Okay, so that's awesome. That makes my life so much easier. Number 3, denormalize for reporting and then compare it. Okay, so the final request from Mirror is basically pulling everything together. Okay, so now the reporting team, they need a view because they want to now plug a dashboard into it. So the dashboard is going to consume data from this view. They want to query it, but they actually don't want to write the joins themselves. Okay, and they don't want to write joins everywhere either because they want their lives to be easier. So Amira, all she wants to see is the difference between the two approaches side by side. Okay, so that's similar to the pattern that we did, I think around section 6. Okay, so we're going to now keep the source of truth normalized, and then we're going to keep the reporting layer denormalized, right? Okay, so let's build the view first. I'm going to type create view, and then I'm going to name this v_census. Let's call this reports. And then I'm going to say as. And I'm basically just going to copy what we just done, all of this. Because why repeat yourself, right? Paste it here. Okay. So that's what I'm doing. I'm going to, maybe I should take this out. Yeah. and then run that. So now I've created a view. Okay, cool. So the view officially exists. So we need to remember that the view itself is not the source of truth. All it's doing is just reading from the tables underneath it. Okay, and those tables are where the real source of truth lives. Okay, it lives in the normalized tables. And you do need to know that a plain view like this just simplifies the query that you write. Okay, it actually doesn't store anything. It doesn't speed the read up. Okay, the version that actually stores the result for fast reads is a materialized view. Okay, and we covered that on day 25, right? Okay, so now we are, let's open up a new canvas. Got so many new canvases opened up. Okay, so we're going to basically do, let's say select region, and then we're going to say select region type, and then we're going to do a count. Okay, we're going to say count as, let's say population. Okay, so now we're going to reference this new view that we just created. So v_census report, and then we're going to group by, I'm going to say 1 and 2, because I can't be asked to type the columns in. Okay, order by 3. So this is what we get. Okay, so cool. Okay, so we're going to get the population per region now. Okay, so let's do it by descending as well, by the way, so that it's from top to bottom. Cool. Okay, so east region's on 7. You can see north with 6, south region's got 4, and west is 3. So you can see that the view hides the join complexity behind that clean interface we just created. That's the payoff that denormalization gives us. So the reporting team gets their answers from one clean query, and they don't even need to touch the normalized tables underneath it. Okay, so what we now need to do is prove the trade-off. Okay, so this is what we're going to do, right? So we're going to do the exact same count, but we're going to do it off the flat table, right? So this was from the view. So now this is going to be from the flat table, okay? And then all I'm doing is changing the table to census raw, okay? Now let's run this. Okay, so you can see that it's given us pretty much the exact same numbers, okay? I probably should even get rid of, let's even say region type, okay? And then get rid of that, okay? Let's do it like that. Okay, so you can see that we're basically getting the same numbers, right? But I'm doing it from the flat table inside, okay? But the data underneath this actually has duplicated addresses and regions on every single row. So if any of those values are wrong, even on one row, then the count is just going to be off, okay? And that's Amira's deliverables done. So we've created normalized tables so that every single fact lives once, and we've created a denormalized view so that the dashboard can read directly from it. Okay, we've also done a comparison just to show that the trade-off, you know, it's okay. Okay, and that's the exercise completed. Now there is an exercise for you to take home. So once you're done, go into the GitHub repository inside the video description, and you're going to see that you can practice normalization, first normal form, second normal form, third normal form, and denormalization. And it's for any level you feel like you're at. So if you feel like you're beginner or intermediate or advanced, there are exercises just for you. So have a go and let me know what you think. So what did we learn today? We covered quite a few things today, but what are the key takeaways from day 18? Normalization, each fact stored once. So remember, normalization is simple, okay? At least the concept is simple. All you're doing is getting one big wide table and you're splitting them into smaller tables. And that's because you want to store every single fact once, okay? And that way, you're not going to have any of the anomaly issues that we spoke about in the beginning, okay? You're not going to have wrong data, you're not going to have like fake data or lost data. And we use the 3 normal forms to build on top of each other, okay? So remember, first normal form says you're only allowed one value in each cell. Second normal form is basically telling you that you have to depend on the whole composite key, not just a part of it, the whole thing. And then third normal form is basically just saying that no column can depend on another non-key column, right? So remember the phrase that we used, okay? So the key, the whole key, and nothing but the key. That's one way of memorizing it, okay? So denormalization. So denormalization helps you speed on the read layer. So remember, normalization helps you speed up your data writes, and denormalization helps you speed up your data reads. Okay, and remember, denormalization is basically trying to add redundancy back. Okay, and you're only adding redundancy back. So when we say redundancy, we're talking about duplicate records and things like that. Okay, you're adding it back because you want your systems to read the data faster. You don't care about writing data faster at this point. You just want to make sure that your data is being read quickly. Okay, so, and that's only on derived copies. Okay, so you can only do that with things like materialized views or even like reporting tables, right? So the source of truth itself, that stays normalized. And then the reporting layer, that's what's going to get denormalized. Okay, so most production systems, they use both. It's basically a hybrid of the two. So you're going to have your normalization core, and then you're going to have your denormalization layer. Okay, so your reporting layer. Okay, so you have to make sure you use both of those. You have to make sure you're using both of those in the right context. And now you have to learn how to choose between them. Okay, make sure you're matching the workloads correctly. Remember, normalize what you write, but denormalize what you read. Okay, so keep your operational database, so like the OLTP side, normalized. That's what you want to normalize. And then the reporting layer, that's what you call like the OLAP side. That's what you denormalized. Okay, so third normal form covers almost everything, right? So third normal form covers almost everything. So only the read layer that your dashboards actually touched needs to be denormalized. And you want to start from one question, okay? So who writes this data and who reads this data? Okay, so try to capture all of that in your mind. But on day 19, we're going to cover recursive CTEs, and that's going to be part 2 of common table expressions. Okay, so we're going to be using them to handle data that has hierarchies. Okay, so things like how folders are structured, or category trees, or any situation where you don't know how many levels deep, okay, it goes until you basically run the query. So the normalized schemas you built today actually are designed for situations like this, okay? So normalized schemas are basically built exactly for the right structures recursive CTEs operate on. Okay, so we're done with day 18. It's quite a lot, but trust me, once you understand this, you're going to be able to help a lot of businesses with some of the issues that they have from a performance standpoint. Because some of them don't really understand, okay, why are my dashboard so slow? Or why am I having issues trying to update data across so many databases? Like, why is it so inconsistent? Why are there so many copies? This video answers all of that, okay? But we're going to be covering normalization and denormalization in data projects in the future on separate videos, okay? So watch out for that. But I want you to stay blessed, and I'm going to see you again. Peace.